Okay, so Isa asked me to say a few things about interpretation. So I wasn't planning to talk about interpretation today, but if you want, I can talk about interpretation. Are people okay with that?
Sir, interpretation of what?
The Copenhagen interpretation
Oh, yeah,
and the many world scenario. It'll be very qualitative. I think it'll be good to have a short discussion on that, okay? Because so far we have actually talked about time evolution, right? So time evolution, it is a unitary evolution. So meaning that it's implemented by unitary operator. So what does that mean? If I take a state psi as a function of time and I look at its norm, this is actually constant. Okay, this is the norm and it's positive, and this is constant. This is one of the problems in your assignment 2, for example. Now, that is what it means called unitary. But in quantum mechanics, there's another kind of, time evolution, which I'm putting in quotes. So this is the evolution that Schrodinger called R2. And this is the evolution which Schrodinger called R1. And this is basically observation. So when you make an observation, something happens to the system. The system after the observation is not the same as the system before the observation. Okay, so, and that time evolution or observation is not a unitary process. So what do I mean by that? What I mean is that suppose that we start with a, say, spin half system, which is in some state, say, C1 plus of Z plus C2 minus of Z, where, of course, we have normalized our state so that C1 squared plus C2 squared is 1. Now, if I observe the SZ the Z component of the spin, what are the values I can expect? What are the results I can expect?
Either of the eigenstates.
Okay, yeah. So we can get plus h bar by 2. In that case, we say that psi collapses to this state. So this state, if you normalize it, then it's just this. And the probability of that happening is C1 squared. That is the Born interpretation. Or we can get minus h by 2, and then psi collapses to minus of z, and the probability of that is C2 squared. And this, so, basically, as far as observation is concerned, this is all we can say, is that right after the observation, say, of x, the state psi collapses to an eigenstate of x. Okay. So this is, and then, again, the evolution of the system starts according to Schrodinger equation from that point onward. So as far as observation is concerned, this is the, Copenhagen. This is part of the Copenhagen interpretation. Copenhagen also says that, So, Niels Bohr was in Copenhagen, and he was the head of the group which pushed forward this interpretation. So Copenhagen interpretation also says that, this is all you can say. You can just say that you can just make probabilistic interpretation in quantum mechanics, okay? You can only make probabilistic interpretation of quantum mechanics. So during that time, there was a very prominent physicist who did not subscribe to the Copenhagen interpretation. Do you know who that prominent physicist was?
David Bohm.
Yes, David Bohm, but someone even more prominent than David Bohm.
Einstein.
Einstein. Albert Einstein did not believe in the Copenhagen interpretation. So what Einstein believed was that there was some sort of hidden variable. So there was some degrees of freedom that the wave function psi did not contain. So Einstein believed that psi was not the fundamental description of nature. There was some hidden variable, and if you had access to that hidden variable, then you could say for certain whether, when you made the observation of SZ, whether you would get this or this, okay? So Einstein, he subscribed not like in a particular, he did not subscribe to a particular hidden variable school, but in general, he was a critic. He was a critic of Copenhagen, and David Bohm, as Nahi said, had a version of quantum mechanics which had a hidden variable. It's a hidden variable theory. So in a hidden variable theory of quantum mechanics, the particle's position and the momentum are always well defined, but they cannot be observed. There's a catch. The hidden variable theory of Bohm or anybody else that is consistent with quantum theory is a non-local theory. So meaning that if you have a hidden variable theory which is like which has multiple particle, and you make an observation or do something to this particle, then its effect immediately is felt on the other particles. So in other words, there is a propagation of information, some sort of information, faster than the speed of light. So at a fundamental level, hidden variable theories are non-relativistic. Okay? Because as you know, in relativity, disturbances cannot propagate faster than the speed of light. However, you can show that at the level of observation, hidden variable theories can be relativistic. Okay, so there's a whole school of thought. Hidden variable theories are even popular even now among certain physicists. So the most prominent of them being Valentini. Okay, so Valentini has his own hidden variable theory, and he has made the prediction that the thing about hidden variable theory is that their observational effect is indistinguishable from standard Copenhagen quantum mechanics. However, Valentini says that in extreme places in space-time, say near a black hole or a Big Bang singularity, hidden variable theories will give you different prediction. And he has tried to develop some observation such that you could glean whether there was a variation from standard quantum mechanics near the Big Bang. So far, he hasn't found experimental evidence in the cosmic microwave background. Okay, so that's a kind of interpretation. Another interpretation is the interpretation due to Everett, so who is long dead now. And Everett, in his PhD thesis, put forward a interpretation which he called the relative state interpretation. And what he said is that if you start with some particle which is in this state, so it's in a linear combination of, say, psi1 and psi2, where psi1 and psi2 are eigenstates, of, say, x, and you make an observation of x, he said that psi does not collapse to this or that. What happens is that, while in this universe you observe, the eigenvalue, say, x1, our universe at that point splits into another universe, two universes. In one universe, you basically observe psi x1. In another universe, you just observe x2. Okay? So, things don't collapse. It's just that whenever you do this kind of observation, the universe splits into two. And so Everett did not give this name, but it is now known as the many world or many worlds interpretation of quantum mechanics. Of course, this is a favorite subject of science fiction writers and filmmakers. And this name was coined by John Archibald Wheeler, who was a very famous physicist, also very famous for being the PhD supervisor of Richard Feynman. Okay? Any questions?
No, sir. I'm starting to see why stuff like quantum mysticism exists. There are lots of interpretations of certain things.
Quantum mysticism is essentially, what's the word I'm looking for? Bunch of baloney.
Yeah.
Okay? There is basically no evidence for, those kind of stuff that people talk about. Now, if you read Roger Penrose,
what's the viewpoint of people? Like, I was in a seminar in Latvia, so there was someone from there who was basically, showing a book by, how the hippies saved physics by, David from, MIT. Like, so basically, there were David. Okay, let me just Google it up.
So, the Tao physics by Capra is a famous one. Yeah, those are, a lot of them are very...
by David Kaiser. Is that an authentic reference to C?
So what is David Kaiser? Is he a historian of physics?
Yeah.
Okay, I mean, historically, those things might have played a role. That's something different, okay? And we don't know whether, so, quantum mysticism is not the same as, say, as the point of view that quantum mechanics plays an important role in human or even sentience in any living being. That's a separate thing. And there are people and very prominent and very well-known physicist like Roger Penrose. And as far as I know, Roger Penrose is an atheist, although he never says so explicitly. They believe that, whatever their personal belief is, that's separate. He believes that, that consciousness is something, has an essentially there is some quantum mechanical aspect to it, okay? And that has never been proven nor disproven. And Roger Penrose's view is very strongly anti-AI. And not only that, he even thinks that, the fact that, quantum gravity plays a role, okay? So those are controversial claims, but, when somebody like Roger Penrose, puts forward that in a very detailed book, it's called The Emperor's New Mind. It's one of the best books I've read in my whole life. And I highly recommend you read it. You will learn things about physics and mathematics that every person interested in physics and mathematics should know. Even if you don't subscribe to Penrose's point of view. So it's a argument against strong AI, okay? So anyway, coming back, having the view that quantum mechanics does play a role in consciousness is not the same thing as saying that, quantum mysticism is bullshit, okay? So I am of that camp. I find a lot of Penrose's argument very, very compelling, his argument against strong AI, but I do not believe in quantum mysticism. That is not to say that there aren't phenomena about the mind that we have not discovered, but what have been discovered is not quantum mysticism. There's a lot of, people like, what's his name? Deepak Chopra and people like that. These people peddle pseudoscience. This is my point of view, and you don't have to take my point of view, but you can, you should make up your own mind and look at these things very carefully, very critically. But I'm telling you what I think, okay?
Yeah, a bunch of grifters selling stuff in the name of unique things.
Yeah, it's just like people are so
I also
gullible.
heard, I also heard similar things. Like when I heard a talk from Lee Smolin, and he had kind of similar views regarding these stuffs.
Yeah, Lee is very, very good. Lee is like, he has done irreparable damage to string theory, but it's his opinion. But he is a very good scientist and a very good philosopher. I like him very much. I know him personally.
I see.
Okay. All right. So shall we carry on?
Yes, sir.
Okay.